Here's an example based on problem 11 from chapter 19 of Bach, Feldman, and DeVoe. Confidence intervals for proportions. I feel like this is almost the most important and maybe trickiest part of the book, taking what we've learned about probability and turning it into a real honest-to-God technique for statistical inference, making conclusions, making precise conclusions. I'm not going to rehash what the book does in terms of deriving this, but I'm going to try and go through an example real carefully. So, in August 2012, Gallup poll found that 46% of a random sample of 845 American adults said that Lindsay Lohan is the best actress who ever lived. And yes, I made that up. Of course I made that up. But let's run with it. Part A. Find the margin of error for this poll if we want 95% confidence in our estimate of the percentage of all American adults who believe this. So the point is not what these 845 American adults believe. It's hoping that they're a sample, they're a representative sample that lets us predict what all American adults believe. So we would guess that somewhere near 46% of all American adults believe this statement, based on what I'm saying. And we'd like to quantify how much confidence we have with that. Okay, so the margin of error for 95% confidence. Okay, well, 95% confidence, we're assuming a normal model. Okay, why? Okay, well, we should have, it's a large sample size, so the large enough sample size condition should be met. 845, the NP and the NQ, P, the proportion is about half, and so half of 845 is way bigger than 10. Okay. Hopefully, if they do their job correctly, Gallup polls knows what they're doing. It is randomized correctly, and they should be independent of each other. And 845 adults is a lot less than 10%. $10, no, 10% of the total population. So we don't run into the fairly rare problem of oversampling a small population and not having independence. Okay, because you're not sampling with replacement. Okay, so we've checked our conditions, and so we can assume a normal model. Okay, and so the 95%, we know the critical z-value for that. Critical z star for 95% confidence. Confidence is z star equals 1.96, roughly 2. That comes from the 68, 95, 99.7 rule. But this is the more accurate value that we're going to use from now on most of the time. Okay, so that means that our margin of error is going to be plus or minus. So it's going to be, well, let's just say our result is going to be 46. Oops, I was already in math mode. 46% plus or minus, it's up here somewhere, there we go, okay, 1.96 times the standard error for this sample. Okay, so we need to figure out the standard error, 46% plus or minus 1.96 times, okay, so that's, remember the difference between standard error and standard deviation. We'd like to know the standard deviation, but we don't really. Even if this is well modeled by a normal model, which it really should be, all the means of different samples, possible different samples we took, we don't really know the standard deviation. But we're going to run with an estimate of the standard deviation. It's probably pretty close. We're just going to take the PQ over N formula, with P being 0.46 and Q being 1 minus that, 0.45. Okay, so that's P hat and Q hat. And then divided by the n. And it's the dividing by the n that makes this whole thing work, that makes this into a relatively small number. Oh, you know what? Since I'm doing this, let's do it 0.46, and we'll translate to percentage at the end. You can get a pretty bad error if you don't do that. So this is really going to be a number that's eventually going to become a percent, but we don't want that quite yet. Okay, so we just need to evaluate this puppy. That's the standard error. Okay, so 0.46 plus or minus 1.96 times 0.0171. Gave it to me in scientific notation, but I didn't really need that. Okay, let's evaluate that. Just kind of going through each step. Plus or minus 0.0335. We probably don't need that last one. 0.34. Okay. So there's our margin of error. And now I'm going to translate it into percent. 46% plus or minus 3.4%. So we took our z star value and we multiplied it by the standard error in the proportion. And I guess I should say SE of p hat, the standard error of the predicted proportion. There we go. That's some more official terminology. And it says that 46% plus or minus 3.4% with 95% confidence is the answer we would report. Okay, so there's the mechanics of it, but what the heck does that mean? Okay, this is the really tricky bit. Okay, this means that if we took many such samples, if we did this a sample of 845 American adults over and over and over again, independently, randomly, different samples each time, then 95% of those samples would fall in the range between, well, 46 minus 33.4% is 42.6%, and would have proportions, let's see, would result in proportions saying that Lindsay Lohan is the best actress in the world, who ever lived. Those proportions would fall in the range between 42.6% and 49.4%. Okay? That's what it really means. And that's an interesting thing. That's a fairly complicated, weird thing, but it's the best we can really do from this perspective. It says that if you did those samples over and over and over and over and over again, the vast majority would be between 42.6 and 49.4%. And we're not sure, we can't be definitely 100% sure that the real proportion of American adults is in these boundaries. But it'd be pretty weird if it weren't in these boundaries, because we know that 19 out of 20 samples would lie in this range. So it's not directly a prediction of exactly how many American adults believe this. What it is a prediction about a bunch of hypothetical samples. But since that's the best we can do, most people take that as saying, okay, I'm pretty sure that the real number is in this region. Okay, so if you want to be 98% confident, will the margin of error be larger or smaller? Okay. If you want more confidence in your result, you can't just say, oh, I'm going to be more confident. Unless you change the study, and in particular, unless you went back and did a new sample with a larger sample size, you can't just say, oh, I'm just going to be more confident about it. If you want to be more confident about it, you've got to have a bigger range. It's got a certain percentage of, all these samples have a certain percentage of probability being between this range. Well, if I want to say, well, I really don't even want to accept this 5% probability of being wrong, basically, or the 5% of the samples that would be outside of the sample range, the margin of error, to be more precise. If I want to have a larger confidence, I need, unfortunately, a larger margin of error. Okay. And to find that, well, we can't use the 1.96 value anymore. That's the only thing that's going to change. We need the z star for 98%. Okay, so we want to find out what's the z star that gets 98%. Need 98% of the area under the normal model to be within, and we want a symmetric interval here from a little bit below to a little bit above, the same amount. So to be within minus z star to z star. Okay, so let's see, that's a little tricky because our inv norm, if we did inv norm of 0.98, that would tell us how to pick a z-score so that 98%, including the left-hand tail, would be included. So what we really do is we need inv norm of 0.99. What we really want is 1%, a 1% tail on the left and a 1% tail on the right, lower than minus z star or bigger than z star. Okay, so if it's a 1% tail on the right that we want to exclude, that's really inv norm of 0.99, and I happen to have calculated that on the calculator. It's 2.326. It's probably more decimal places than we need, but it's okay. Okay, So that means 99% of the area will be below z star is 2.326. So if we do the symmetrical version, it means that 98% of the area is within z equals minus 2.326 to z equals 2.326. Okay, so that's going to be our z star value. So that's a little bit tricky, but it's doable. Okay, and so now the new margin of error is just going to be exactly this calculation. The standard error is the same because I haven't changed the probability or the sample size. I'm just changing this guy to get more confidence, to have less probability that I'm accidentally in the tails. I just do this. I wonder if this will actually compute it. Huh. That's interesting. I think it just interpreted the plus as a plus or minus. I really want this one. Okay, so that's about 4%. So we basically got 46% plus or minus 4%. So instead of the 3.4% margin of error to be kind of wrong 5% of the time with this process, now I'm only going to be wrong 4% of the time, or more precisely, only 4% of these kinds of random samples will be outside. I'm sorry, only 2%. Looking at the wrong percentage. Only 2% of these kinds of random samples will be outside the range 46% plus or minus 4%. Okay, so this is an additional little thing they don't talk about much in the chapter, that if you go outside of our usual numbers, we need to do an infinorm, and it's a little tricky to do that. Okay, and then in general, if I wanted to get a smaller margin of error, and if I wanted to say, oh, I think it's 46% plus or minus 1%, well, we're not going to be very confident of that. A lot of the samples are probably going to go outside of that. And that's going to be less confidence in the interval. If you want to remember how it works, just remember there's no such thing as a free lunch. You can't have a smaller margin of error and greater confidence unless you do more work, namely have a bigger sample size.